Alrighty everybody, we're going to be taking a look at electromagnetic induction. I'm going to walk you through a conceptual understanding of electromagnetic induction. We're going to talk about what Faraday's law and Lenz's law are, what those two laws are and how they represent the idea of magnetic flux. And we'll also relate the concept of magnetic flux, which is helpful for being able to understand and be able to numerically predict a value for EMF. But I also want to talk about how understanding the magnetic force on the charges in the situation help us to have a conceptual understanding of why there is a current or why an EMF gets generated in the first place. So to do that, let's take a look at the situation. We have here a copper bar or a conducting bar, and let's say it's moving to the right through this magnetic field. So there's a uniform magnetic field, and we'll say that the bar is moving to the right with some speed v. Now we know that the bar is actually made up of charges, so there's negative charges in the bar and positive charges in the bar as well. Those are all moving through this magnetic field. And because of that, there's a force that each feels. We can use the right-hand rule. The charges are moving to the right, the field is into the screen, and so now your palm is up, and then your middle finger is going to point towards the top of the screen, and so the force on these positive charges is going to be upward. And the force on the negative charges, since it's opposite, is going to be downward. So let me write that. Actually, let me change this style. Let's make that purple or pale blue or something. There we go. That way I can draw the magnetic force is upward for those, and the magnetic force is downward for those. This all derivation is also done in one of the AP Classroom videos, so you don't have to stick, you can watch it there too. I forget which one. Now, the positive charges don't move, but in a conductor, the negative charges will move. And so these negative charges, right, like this one here, it'll start to move downward. This one will start to, oops. Too much stuff on my screen. That's not helpful. Anyway, the negative charges will move downward. The positive charges will stay where they are. Yeah, I don't actually want to select that right now. Thank you, though. The positive charges will stay where they are. The negative charges will move downward. And so what we'll end up seeing is that these negative charges collect towards the bottom, but they don't move far, because as they move downward, then there's a negative charge at the bottom of the rod and a positive charge towards the top of the rod. So the whole rod itself becomes polarized, where we have an overall, let's do an overall positive charge up here near the top, okay, and an overall negative charge down here near the bottom. Now inside that rod, that means that there is going to be an electric field that gets generated because of separation of charges. Right? An electric field is going to be equal to the potential difference divided by the length of the rod L, if this rod is of vertical length L. So the potential difference, that's, because you're separating charges, you're grouping negative charges at the bottom, positive charges at the top, there's a higher potential at the top and a lower potential at the bottom. So that creates an electric field. That electric field is going to apply a force that is going to be upward on the electrons. Right? There's an electric field between those two charges. It's like between two parallel plates or between a positive and negative charge. There's an electric field that gets generated upward, or electric force that gets generated upward because of the separated charges. Now, remember, this whole rod is moving to the right. It's moving horizontally. And so the charges will separate because there is a magnetic force. The electrons can move, and so they do move. This wouldn't happen in an insulator. But in a conductor, they can move, and so they move downward. They will gather at the bottom, sort of bunch up more towards the bottom, leaving some protons towards the top that aren't canceled out by electrons because electrons have shifted. And that'll happen until those two forces are equal to each other. And so, as we can see, if we were to set those two forces equal to each other, we say that the electric force equal to the magnetic force. Well, the magnetic force, everything is perpendicular, so we don't have to worry about that pesky sign theta, but QVB, right? And then the electric force is going to be Q times E, but we also said that that was Q times delta V over L equals Q times V times B. Now the Q's very nicely cancel, so it doesn't matter whether we're talking about negative or positive or electrons or some other charged particle. It would be the case. This is essentially our velocity selector kind of problem. And so we find that the potential difference across the two sides here is given by B times L times V. And I leave it in that format specifically because that's going to be helpful to us in just a little bit. Okay, but B times L times V is the potential difference between the top and the bottom. Okay, now by itself, that's not terribly interesting, but let's imagine that we had a situation in which we were able to have these two stationary long wires, like these two rails, essentially like railroad car rails, that are bridged and connected on the left-hand side. And then we have this bar that goes sliding across them, conducting bar going sliding across them. Well, we just said that we're setting up a potential difference. And so that's kind of like having a battery connected like that, right? There's a higher potential on one end and a lower potential on the other. Oops, dropped my pen. And so the whole thing, right? Oh, not that. This is not as easy as I wanted it to be. The whole thing is moving to the right like this. The whole thing is. And so what we end up getting is we end up getting a current that will flow through this wire in this direction. This current flows because we have it established some potential difference, delta V, or we can begin to call that an EMF if we wanted to. Because remember, batteries, we say they provide EMF. Anything that sort of causes electrons to flow, we'd call that an EMF, an electromotive force. It is the same thing as a potential difference oftentimes. And so it's just basically this impetus, this push given to the electrons in the circuit. And so we're going to have current flow around this. And that current, it turns out, will create a magnetic field inside this the left-hand end of this wire where it's boxed in, right? We have current going around in a loop, and just like we have current going around in a circular loop, it creates a magnetic field. The magnetic field on the inside is actually going to be directed upward. So I'll put that in purple. So we'll have a magnetic field created inside this region that is actually coming out of the page. And you can verify that with the right-hand rule. Now, we can look at this and think of it in terms of, the potential difference caused by the force on the charges and separation and, an internal electric field being set up, and that internal electric field multiplied by the charge equals the force moving downward on the charges because of the magnetic field. That's all true. But it can be a little bit more helpful to us to think about this in terms of what we call magnetic flux. Okay, what we call magnetic flux. And magnetic flux, we give the symbol capital Phi, or maybe you call it phi. I don't know. Do you call it pi? If you call it pi, then you probably should call this phi. But if you call it pi, then you probably should call this phi. Anyway, we call it magnetic flux. And this is essentially equal, the main idea, the thing that you can call this is the number of magnetic field lines that go through an area. It's a little more complicated than that, but that's a very quick and dirty understanding of what it is that pass through an area. And this is what helps us understand where Faraday's law fits into this. All right, so if I were to highlight a section here, say in purple, okay, then this section here, let's say it starts off this big, because this whole thing is over there, right? As this rod slides to the right through this magnetic field, and remember, as it does that, it is going to be generating a potential difference across the two sides because the charges will separate, because the magnetic force exists on the charges and they act in opposite directions, but the protons can't move, the electrons do move, etc. Okay, so there is a potential difference that exists across those. But as this slides across, right, notice that it starts off here, and there are 1, 2, 3, 4, 5, 6 magnetic field lines through the area that is highlighted in purple here. But as this thing slides to the right, notice that the area is getting bigger, and so now there are 1, 2, 3, 4, 5, 6, 12 magnetic field lines going through that area. And so we would say that the magnetic flux, what happened down here? Goodness gracious. Oh man, my life is good. That can come down here. Oh, undo. I know what I'm doing, I swear, I promise. I'm very, very capable. I forgot the dot of my eye, apparently. Okay, magnetic flux, capital letter phi. It's a Greek letter. Okay, so that magnetic flux is increasing, right? Because the purple area here, there were 6, now there are 12, and if you continue, then it'll be 15, and then 18, etc. As that rod moves to the side, then it's going to be allowing more and more magnetic field lines to pass through that area that is defined as the area within the two wire rails that are horizontal and that vertical bar that's moving to the right. And so that's the connection here. That's what Faraday's law is talking about. It talks about magnetic flux. So let's take a little bit closer look at magnetic flux. We'll go over, I have this quick 3D model that I made. And so I have here, we can see that if I were to change the orientation of this, we can see that this is actually some magnetic field lines that I've modeled in blue. And then there's this orange ring, which is to represent a conducting ring. Okay, I'm gonna set it to that view mode. And so if I were to just move this horizontally, right, or vertically around in here, if I were to just move this around, then we're not really changing the number of magnetic field lines, because as soon as one drops out, then another one pops in on the other side. And so in a uniform field, just moving it around, I'm not going to change the total number of magnetic field lines. Okay. Now I might, because I've drawn them so discreetly, I might be able to get sneak one out and the other one doesn't come in yet, etc. But you get the idea that the magnetic field passing through this ring is going to be the same. But imagine if I were to change the radius of this. If I were to make it smaller, we see that drastically changes the number of magnetic field lines that are passing through that center area, through that ring. If I were to make it larger, then I can increase. So clearly the area of this is going to make a big difference, right? The area of the ring, right? Also, where it is, if I were to move it out to one side, now there are only 3 or 4 magnetic field lines coming through. But if as it enters into this magnetic area of magnetic field, now it's got some number, and as it exits, now that number is decreasing. The number of field lines, the number of dots that are passing through. And so if I were to, move this thing into and out of this magnetic field, then I would be having some number of magnetic field lines that are changing. Once it's in that magnetic field in uniform, then the number stays the same. So we would say the magnetic flux is constant. And then once it exits out the other side, then that magnetic flux would decrease. Okay, so the magnetic flux depends on the size, the area that you have, right? It depends on whether the ring is fully inside a field or external to a field. It would also be affected by the density. I can't actually, my model won't let me do it right now. But if I were to, have twice as many dots here on the screen, like twice as many magnetic field lines because the field is stronger, then very clearly we would have more magnetic field lines going through my area, which would mean a greater, what we call magnetic flux. But another feature that I want to take a look at that's also important to recognize is how the orientation makes a difference. And so this ring here, if I were to change the orientation of it, right, if I were to rotate it by 45 degrees, right, relative to the magnetic field, then again, when I look at it from the front, it's now got a smaller profile from the front view. And so there are fewer magnetic field lines that are passing through there, right? If I were to rotate it again, another 45 degrees, and we look at it from the front, we see that there are actually none. There are no magnetic field lines passing through that anymore. They're all parallel to that surface, right? They're not passing through the area there at all. And so the magnetic flux in this case would be 0. And then if we were to continue to rotate this through some other angle, oops, that would be tricky. There we go. If I were to continue to rotate this through some angle, we'd find that it actually got bigger again, and then 0, and then bigger again, and then 0. And so it would go through this cycle of getting larger and smaller as the number of magnetic field lines, or the amount of magnetic field passing through that ring. Oh, I made it a weird shape now, didn't I? Okay, well, that's how it works sometimes. Anyway. So that is, I wanted to show that that's a visual representation of what, oh wow, that's, okay. Well, this is why you don't try and do 3D drawing on your iPad while screen recording. It's just embarrassing. I mean, that's cool and all, but not what I wanted. Anyway, I'm done with it anyway. Just isometric, there we go. All right, so moving on, back to... Back to our notes. So the magnetic flux is changing. The number of the magnetic field lines that are passing through the area changes. And what Faraday's law tells us is that when that happens, when you change the number of magnetic field lines passing through an area, there will be created an EMF so that the magnitude of the EMF is proportional to the rate of change of magnetic flux, the time rate of change, okay? So that's what we call Faraday's law. Faraday, named after Michael Faraday. Okay, Faraday's law says that the EMF generated is directly proportional to the time rate of change of the magnetic flux. Time rate of change of magnetic flux. Now there's magnetic flux, we have to understand it a little bit better. We said it depends both on the area, we saw that. If I change the area, then it changes the number of field lines, and also on the field strength. A stronger field or a weaker field would have a different number of field lines passing through the same area. And also on the orientation, right? And how those two are related, how those two are oriented relative to each other. And so what we actually come up with mathematically is that this is equal to b times a times cosine of the angle theta. And that theta there is going to be a little hard for us to visualize. Essentially, what I want you to do is I want you to think about that if you had a ring, okay, of some kind, and I'm going to try and draw this sort of quasi three-dimensionally, okay. If you had a ring, then the angle theta is going to be, let's draw, this is the primary axis of this ring. So imagine that's like the midline of the ring, the axis around which it rotates. And then imagine an area vector that is along that axis and pointing out according to the right-hand rule. And so if I were to curl my right hand around this axis, my thumb points to the right. And so that means I'm sort of taking a look at this going in that direction and that direction. So if I wrap my fingers around it that way, my thumb points sort of off diagonally to the right. If I have a magnetic field that is also in this area, passing through, right, some external magnetic field like that, then theta turns out to be this angle right there. It's the angle between the axis of the area, and that's easy to see if it's a circle. If it's just a plane, right? If it's a plane like this, if it's a rectangle or something, then the axis to this area would be, this is the A vector is pointing out at us. We use our right hand, we wrap our fingers around this thing counterclockwise, our thumb points up. And so our A vector is upward, and our magnetic field is going into the screen. And so the angle between those two is actually 180 degrees for this case. So theta equals 180 degrees. Because the area vector, we don't really have to ever treat it this way, but it helps to understand, sort of visualize what we're talking about, is that if you imagine sort of like, the normal to whatever surface, the area, imagine that as an actual physical surface, and A is a sort of the normal vector out of that surface. Then magnetic field is going parallel or anti-parallel, gives you a maximum value because cosine is going to be 1 when theta is 0 or 180, -1 when it's 180. And so this flux is a maximum value when the axis of the area and the magnetic field are lined up. And we saw that with our 3D simulation, which I won't go back to because I messed it up. Clearly, right? And so this relationship here, right? This theta, this phi is b times a times cosine theta. We are not in this class going to have to worry about this. Okay, that is not going to change for us. I won't give you any problems because it becomes very quickly a calculus problem for you to have a changing angle. Conceptually, right, if you rotate a ring through a magnetic field, then it will generate a magnetic flux generate an EMF because the flux is changing. That is true, and that's how that's how generators use electromagnetic induction to create voltage in a wire, is by either having the wire rotate through a magnetic field or having magnets move around a wire. All right, so this changing flux. Now, this changing flux can be caused by a change in B or a change in A, or in the change of how much area is in the magnetic field. And we'll see that in just a moment. So that's Faraday's law. It says that the EMF being generated is the change in flux divided by time. And then there's Lenz's law, which says a minus sign right there. And that right there, that's Lenz's law, named after Lenz, another white guy. And Lenz's law says that the current produced by an EMF will oppose the change in magnetic flux. Not oppose the magnetic flux, oppose the change in magnetic flux. All right? So that basically means if you have more dots, the current will produce X's. Okay? So if you are getting more dots in your area, like if there's more magnetic field lines coming out of the area in the positive direction towards you, out of the screen, then your current, whatever direction that is going to produce X's to oppose the more dots. So every dot you add, you're going to have an X to counter it. You're opposing the change. If you have fewer dots, then it's going to produce dots, right? And then the same thing for X's. So fewer dots, so fewer magnetic field lines coming out of the screen towards you, then the current, whatever current direction is going to be, that current will be in the direction that produces more dots. Okay, let's take a look. Okay, so we said up here that this bar moving to the right through this magnetic field will produce a a positive potential at the top of the bar and a negative potential at the bottom of the bar. So it's just like having a battery wired up in this direction. Now, if I were to say that the current is flowing in this direction, around anti-clockwise, then that is going to produce a magnetic field, because if you have a current that is going in a counterclockwise direction, then the magnetic field is going to be produced coming straight up out of the page. The induced magnetic field. Okay, because there's an induced current caused by this bar moving to the right, the area is getting bigger. As I go to the right, I'm adding more x's to my area, and so I'm going to add a current that is going to produce dots, basically a magnetic field that is coming out of the screen towards me, not into the screen. And that's opposing the change. So we can think about it in terms of the magnetic force acting on the charges in this bar, which produce a positive potential at the top of the bar and a negative potential at the bottom of the bar. That produces a current in that stationary conducting wire, that rail, sort of those two horizontal lines and that vertical line that connect them on the left. So if you have a potential difference, then that's going to create current that flows. That current is flowing as a result of the separation of charges. You could also think of it in terms of magnetic flux. And as the bar on the right-hand side moves to the right, it is going to be increasing the area that's in the magnetic field. The magnetic flux going into the page is going to increase. And so a current that opposes that increase into the screen, so that would be a current that is going to produce out of the screen magnetic field, is going to be created. Now, we say that in Faraday's law, it depends on the time rate of change. So the more quickly we change the flux, the bigger the EMF should be. Let's go back up and take a look at our voltage. Our voltage here is produced as B times L, which are both constants, multiplied by V, how fast I'm moving. Now that V is a delta X over a delta T. B times L times delta X over delta T. And if I take a look, my L times delta X, that right there, that's going to be a change in my area, isn't it? Some length, height, multiplied by some horizontal movement, delta X, that's a change in the area. How big did my area get? Well, it's my horizontal displacement multiplied by my vertical length. And so then this becomes B times the change in area all over the change in time. Well, that right there is the change in the magnetic flux, because magnetic flux is B times A, times the cosine of the angle between the axis and the magnetic field. That's constant here, so we can ignore it. It's 1, or it's negative 1. Okay? And the fact that it's negative 1 tells us that the change in the magnetic flux is going to be an increase in the negative direction, and so our EMF is going to be producing a current in the positive direction, which produces the positive direction. It's anti-clockwise because it's sticking up out of the screen. That's the positive Z direction. So we have an increase in the flux in the negative Z, but then we have an opposite sign there, the negative. And so if the increase is in the negative direction, that means the EMF is going to be produced in the positive Z direction, so coming up out of the screen. So that is a connection between magnetic flux, Faraday's law, and the idea of magnetic force. The two are two ways of looking at the same problem. In fact, any magnetic flux changing problem, any Faraday's law problem, you can always look at it in terms of a magnetic force acting on charges in whatever situation you're talking about. In fact, I'd like to go through that with you and see how that's true. All right, so here's a classic problem. I've drawn I have here a bar magnet, and the bottom of it is the north and top of it is the south. And I have here a picture of a coil. I've cut it in half, and so we can see only half of the coil. But imagine it has a three-dimensional coil sticking up sort of half behind the screen, half in front of the screen. It's oriented, perpendicular to the screen. Okay, or it's axis is actually parallel to the screen. So if I were to have this magnet come down towards through there, okay, one interpretation of that is we see that the magnetic flux is changing. Right now there are essentially no magnetic field lines going through that coil. And then I get down here, I have 2 magnetic field lines going through there. I have 4 magnetic field lines. Now I've got even more. Then I get through here and I'm halfway. And now actually there's no change in magnetic flux because the same number of field lines. And now I'm decreasing the number of field lines that are passing downward in the negative y direction. The number of negative y field lines is decreasing as this comes down. And so according to Faraday's law, if I want to take a look at this from a Faraday's perspective, and maybe that's helpful and maybe that's not, right? Faraday, then we see that the negative y flux increases, and as a result, what that means is we should get an EMF that produces a current that produces a magnetic field in the positive y direction. Okay? The flux in the negative y direction increases. Take a look at that again. This thing is moving downward. The magnetic field lines are pointing down. And so the flux going through this ring is increasing in the negative y direction. Okay? Flux itself is not a vector quantity, but the field lines that are going in the negative y direction is increasing. So that means that according to Faraday's law, right, and Lenz's law, Faraday's law says how quickly that's happening should produce an EMF. The EMF is proportional to how quickly the flux is changing. Lenz's law says that it should be in the opposite direction. What is the opposite direction to down? Negative y? That would be in the positive y. What direction of current would I need in order to produce a magnetic field that is upward? Well, I think that you can see that it would have to come out and around this way and go back in. Okay? So we'd have to be going into the page on the left, so we'd have to have a current that is going that way into the screen on the right-hand side. And on the other side, we'd have to have a current that is coming out of the screen. So looking down and above, it would be anti-clockwise, and then the induced magnetic field would then be directed upward. Okay, because the magnetic flux is increasing downward, that means we want to have a magnetic field generated upward to oppose the change. All right, well, let's take a look at that from the forces standpoint. Okay, just from the forces standpoint. Okay, so I'm going to erase my red magnetic fields, or my red current, and see what happens with just my forces. Now, I want you to imagine, got a little bit more, there we go. Okay, imagine that this magnet moving downward is exactly the same as this coil moving upward. Do you see that? That the coil moving upward is exactly the same as the magnet moving downward. Those are just like, whose side are you on kind of thing. Okay, so as this coil moves upward, imagine right at that moment right there. Okay, it'd be easier to see at that point. Right at that moment right there. Here we have these charges in this wire that are moving upward, and at that moment there is a magnetic field that is pointing that way. This is true for any point before this also, but this makes it kind of the easiest to see. Again, we have a velocity moving upward, and we have, in this case, a magnetic field pointing off to the right. Okay, the two of those, right? Use your right hand rule. Velocity, charge moving upward, thumb points up. On the left-hand side, the magnetic field is pointing left, so your finger's pointing left, and now your middle finger points right at you, doesn't it? And so the magnetic force is pointing out at you at the screen. Do the same thing on the right-hand side here. We have the velocity pointing upward, the magnetic field pointing to the left, and then we have a force going into the page in the negative z direction? Well, if you were to push on charges, remember that current is the movement of positive charges. We don't allow positive charges to move, but we can pretend that they do, and it behaves the same as if a current does. And what does that result? Well, that means that this magnetic field passing through this coil is going to produce a force that comes out of the screen on the left and into the screen on the right. And if you were to do this at any point along the way, you would convince yourself that the magnetic force is going along the coil in a circular pattern. Any point you pick, three-dimensionally, rotate this thing around three-dimensionally in your head if you want to, or just trust me, you get that all of the charges are being pushed around anti-clockwise. And that produces a current anti-clockwise because in the conductor, charges can move. No, it's true, the positive charges are not actually moving. Right? Remember that, but we can pretend. And if you were to do this with electrons, you'd find the electrons just go the other direction. And so you'd have electrons moving clockwise, which results in a counterclockwise traditional current. Okay, so classical current is anti-clockwise here. Just, okay, convince yourself that that's true. Okay, so the forces, we have the moving charges. Now remember, they're not actually moving because the ring is stationary, but relative, right? Charges moving relative to the field. I should probably put that instead. Ooh. To the field. Experience a counterclockwise force. Okay, so Faraday's law tells us that as the flux in the negative direction increases, then Faraday's and Lenz's law, I should give him credit too. Okay. As the magnetic field and magnetic flux in the negative y direction increases, then we should produce a current that would have a magnetic field in the positive direction. That's a counterclockwise current. Looking at it from magnetic forces point of view, then the charges moving relative to the field are going to experience a counterclockwise force, making them move. It's exactly the same thing. The result is the same, but two different perspectives. Okay. Now let's take a look at what happens when the magnet is right passing through the very center of the ring. So I'm going to erase all this. Okay. So as the magnet is passing right through the very center, okay, we notice that the magnetic flux is essentially unchanging, right? At the very center here, right, we have no change to the magnetic flux because from one moment to the next we have, it looks like 1, 2 lines on each side, 4 lines that are going upward at this point, and we have some lines that are inside this magnet that are going downward, and so there is no actual change to the magnetic flux, okay, at that moment there. So taking a look at Faraday, so this is situation 1, situation 2, right at the very center, no change in flux, and so that should result in no current, no EMF and no current. So if you were monitoring the current in this coil, you'd notice that it drops to 0 for a moment as soon as the magnet is halfway through. Well, take a look from the forces perspective. Remember that our velocity of the particles or the charged particles is upward because we're modeling this as the coil moving upward through the field rather than the field moving downward through the coil, but they're the same. But look at the magnetic field direction right there. Look at that, they're parallel. And what do we know? That if the velocity of the charges in the field are parallel, then there's no force because there's that sine theta in there. And the 0 is the angle between the two. And so we have, QVB sine theta is 0. And so we have no force. No force means no current because the charges aren't being pushed around. There is no force acting on them. Okay, so taking a look, this will be situation 1. Situation 2, the relative velocity and the magnetic field vector are parallel, which results in no magnetic force. Okay, no magnetic force there. So the same idea, looked at it from two different perspectives. And then thirdly, we can take a look as it's exiting. So this would be as it exits the magnet, as the magnet is exiting the coil of wire. Now we're going from 4 magnetic field lines going downward to 2 magnetic field lines going downward. And so what we end up with is the magnetic flux downward is decreasing, not increasing. So the flux is decreasing in the negative y direction. And this will result in an EMF and in a current that produces a magnetic field in the negative y direction to oppose the change, right? To oppose the change. The change is that there are fewer field lines going downward. To oppose the fewer field lines going downward, we have to put more field lines going downward. And what is that going to be? Well, using our right-hand rule, we can see that the current then has to be the opposite direction, right? The current has to be going clockwise when viewed from above, right? So the current is going to be coming out over here and going in over there, going out and going in. The exact opposite of what we had at the top. Here we had a magnetic field in the y direction, positive y, at step 1. Now we have in the negative y. So if you were monitoring the current in this coil of wire, you would find that it was going one direction, counterclockwise, and then as the magnet passed through, it would go to 0, and then it would become clockwise because it would go back the other direction. Okay. Again, taking a look from a magnetic force perspective, let's take a look what's going on there. I'll back this picture up a little bit to that spot right there. Now we still have a velocity that is going upward, right? We're imagining this coil of wire moving upward through the magnetic field. At that point, the magnetic field is actually pointing inward on both cases. And if you were to take a look, use a right-hand rule, then we'd find that the magnetic force is actually inward on that side, and the magnetic force is outward on that side. And you would find at every point along the way in three-dimensional space that the magnetic force is perpendicular to both the velocity and the field, and that's going to be directed around this coil in a clockwise manner when looked from above. And so here we have the charges moving relative. I'm just going to copy and paste this, even though my handwriting is awful on this one. You know, I'm trying to make this brief and it's not working, and I just copy. It's okay. It's okay. Everything is going to be fine. The charge is moving relative to the field experience a clockwise force in step 3. So the same exact result, but we can look at it and think about it from two different perspectives. What is happening to the magnetic flux? How is Faraday's law and Lenz's law interpreting that? And then also the magnetic forces. How is that going to determine the direction of the moving charges? Now, remember that positive charges don't move, but anything that happens to the positive charge, the exact opposite happens to the negative, and so it goes in the opposite direction, and the opposite direction of the negative charges that are moving is what we call the direction of the current. All right, I'm going to do another one of these in a bit that includes some discussion about some animations that I made, the 4 main ways that you can change the magnetic flux through something, and then how those can be interpreted using forces as well. All right, thanks so much.